Good wishes, respected professor. My name is Dinihal Raj Reddy and I'm holding roll number X233176112. And here I am going to present my project on accurate and efficient short-term solar power forecasting across climatic regions. And coming to my introduction, yeah. Solar photovoltaic power is one of the fastest growing renewable energy sources due to its scalability and rapidly increasing cost. However, solar output is highly variable. It depends on factors like sunlight, temperature, and weather, which changes constantly. And these challenges is finding models that are both accurate and computationally efficient so they can be deployed in real time across diverse regions. And coming to the problem statement, uh, current forecasting models faces a trade-off like some of the high accurate but require heavy computational resources. Other are efficiently but less accurate in various climates. My research question is actually on, can a GRU model integrated with an attention mechanism outperforms existing models in terms of accuracy, efficiency and adaptability across different climatic regions or not? And actually, my aim and objective is on to study design a model that is both lightweight and accurate. So I want to develop a GRU model, enhance it with attentions to focus on critical time steps in the data. I mean, comparing it with against machine learnings models like random forest, XGBoost, and like GBM, as well as deep learning models like artificial neural network and standard GRU. And using these data sets from multiple countries, I actually used Norway, Brazil, India, and Australia to test my adaptability. And coming to my motivation, I I was motivated to research on this project because as the growing need for real reliable forecasting tools that work even in low resource environments. Like while transformers based models achieve high accuracy, they are too resource intensive for many practical deployment. And the GRU plus attention approach offers a balanced trade off, maintaining an accuracy while keeping computational resource requirements low. And coming to my literature review, here in my literature review, we see that machine learning models like random forest and XGBoost compute patterns well but struggle with the temporal dependencies. And LSTM models can learn sequential but are heavier and prone for overfitting. And transformers can handle long sequentials but require huge data sets and computing power, as these gap for models are accurate, efficient, and interpretable and valuable across different climates. And coming to the GRU plus attention model, GRU is actually a gated recurrent unit. It is simplified version of LSTM that trains faster with fewer parameters. By adding the attention mechanism, the model can focus more on the important like time steps such as midday peaks or sudden weather changes rather than treating all inputs equally. This combination improves both accuracy interoperability with while still being suitable for deployment on edge device of low power systems. Coming to my methodology, 1 minute. Coming to my methodology, the data includes hourly measurements of DC and AC power, temperatures, irradiations, and energy yields collecting from Norway, Brazil, India, and Australia. Coming to my code, uh, this is the code I worked on, and here I imported my data set and I check for the null values and I reduce the null values in this code here. And later, these are the data types in my data set. I'm like date, it's in object, time is in integer, date and time in object, sort of. And here, uh, I converted the dates and extracted dates in months, years, and days, sort of like this into day and month and year. And and here I drop the unnecessary columns in this code. And then after I have implemented the plots for the columns like DC power, AC power, ambient temperature modulation, module temperature, the remaining with the DC power, I mean like with the frequency. And here are the plots that I got. This is the graph between the DC power and frequency, AC power and frequency, ambient temperature and frequency, and the remaining simultaneously. And this is the plot between the DC power and irradiation. And here we can see that these blue colors dots are the Norway's, and this orange is Brazil, green is India, and red is in Australia. This graph is between the DC power and irradiation. And later, this code works on the DC power versus ambient temperature. Then after I worked on the monthly and month-wise in the country for various countries like Norway, Brazil, India, and Australia. And here we can see that in starting months there is a low temperature which started from 7.5 in the Norway, as we know that Norway is a very cool place. And later in the middle of the year, I mean like in middle of the months like 6, 7, yeah, there is a high temperature which nearly touches of 23. And then later at the end of the year and it again drops to nearly 7.5. And we can see that the Australia is a hot area and its minimum, its high temperature in the starting year is nearly 23. And then after in the middle of the years, it was nearly reducing to 18. And then after it was again gradually increasing at the end of the year to 23. And later I have worked on the times of the countries, as we can see that at the late nights uh, all the countries are in low, I mean like very least temperature, and in mid, I mean like in middle of the day, we can see that the Norway is nearly touching. Oh, sorry, this is not that. This is the DC power distribution by time and country, and this is the time, and this is the DC power. As gradually the time going into the middays, the DC power is getting increased, and getting into the late nights, the DC power is getting decreased as they can't have the high temperature at the late nights. And later, and this is the uh, pairwise relationship between continuous variables, which all the columns that I got in the data sets. And later, I used the outlier detection, where outlier model is a method or algorithm that is designed to detect and handle outliers in the dataset. And here I in my dataset there are no outliers in the DC power, AC power, but I got some outliers in ambient temperature, modulation temperature, and daily yield. Then after I worked on these columns and I reduced the outliers using the capping. And then after I plotted the graph between in which I got outliers like ambient temperature, module temperature, and daily yield. And these are the graphs of the capping, I mean like reducing the outliers. Then after I tested, I mean like normalized the code and tested and trained the code. Then after I used the machine learning models like random forest, light GBM, and XGBoost. And here uh, in the XGBoost, I got the MSE. I trained the model, and after testing through random forest. I got mean square error as 19, absolute error as 2.7, root mean square error as 4.3. And these are the estimators versus mean square error. And this is the machine learning model of light BGM. And for this light BGBM, I got the mean square error as 36, absolute error as 5, and root square error as 6. And these are the hyperparameters for that. And for the XGBoost, I got mean square error as 30, absolute error as 4, and root square mean square error as 5.5. These are the estimators graphs again. And here I use this is the deep learning model. Uh, Here for the deep learning model, I choose the artificial neural network because artificial neural network is good in communicating with the tables. And here I use the min max scaling, as min max scaling is a data normalization technique used to scale futures for the to the fixed range. After using the artificial neural network model, and here I trained and I predicted the predictions and perform the inverse transform. Here I got the loss as 2.0 as minimum using all the epochs, and I got the mean square error as 1.2. This is the training versus validation loss. Then after, uh, this is the normal GRU model. Presently, the present using GRU model. I trained it after performing the predictions and inverse transform. I got least loss as 3.7 and the mean square error as 2.08. And this is a more training versus validation loss for the yeah, loss and epochs. And then after here, I performed the GRU model with the actual attention model. I mean, like I included the attention mechanism here. I trained the model and performed the predictions and inverse transforms. And with the epochs, I got maximum loss as 1.02 and then after 9.9. Then of here, I got the least mean square error as 0.53 and absolute error as 0.53 and root mean square error as 0.7, which is far least than remaining machine learning and deep learning models and the GRE model too. Here, this is the graph between the training loss and validation loss, and this is the graph between GRE plus attention. I mean, like mean square error over the epochs, and here, this is the GRE plus attention actual and predicted for the first 200 samples. Yeah, coming to the results. In results among the machine learning models, random forest given the good absolute error as 2.67. Uh, Coming to the deep learning model, artificial neural network given the best readings as 0.86. But as we are working on the GRU plus attention, it has given an absolute good results than other models like 0.53 as MAE, 0.53 as MSC, and 0.73 as root mean square error. Coming to the conclusion, in conclusion, GRU plus attention model is accurate, efficient, and scalable for solar forecasting. And in futures, it can be used for incorporate weather forecasting. It can be added uncertainty, qualificational, and explainability. And it is also used for deploying edge and IoT devices for real-time use. Thank you very much for giving this opportunity. Thank you.